Okay, so in this video we're going to talk about the last of Newton's three laws, which is Newton's third law. So just to recap, we so far have seen two of Newton's laws. Newton's first law says that an object at rest remains at rest, and an object in motion remains in motion at constant speed along a straight line unless acted upon by a net force. Okay, and we use that to great effect in drawing free body diagrams and also solving second law problems. Then, of course, we have the all-powerful Newton's second law, which, most of this unit is about the second law, F net equals ma. Newton's third law, kind of like the first law, is mostly a conceptual law. And it does have a lot of really important implications, but with that being said, most of the problems that you might see using the third law are usually conceptual problems using very few calculations, or maybe just a little bit of calculations. Okay, so let's take a look at Newton's third law. Here's what the third law says. For every action, there is an equal and opposite reaction. That's it. For every action, there's an equal and opposite reaction. Now, let's focus in on this a little bit. At first, you might be thinking, what does that mean, action? Because all of the other laws talk about forces. So, just to clarify, when he says action, he means force. And when he says reaction, he's also talking about a force. And so the third law still has to do with forces. Basically, you could rewrite this and say for every force, there is an equal and opposite reaction force. Now, just to be really specific by what equal and opposite means, in case it's not obvious, equal meaning same magnitude, and opposite meaning opposite direction. Okay, and specifically, Newton's third law is talking about the interaction between two specific objects. Okay, so the most specific way to phrase the third law would be something like this. When any object A puts a force on any other object B is going to put an equal and opposite force back onto object A. Okay, so when you're talking about Newton's third law, you're always talking about two objects and the action and reaction forces between those two specific objects. And again, this seems to be kind of a common sense type of law, but a lot of the phenomena it explains actually kind of defy human intuition, as we'll see. Okay, so pause there and make sure you add that to your notes, and we'll do a few basic conceptual examples. Okay, so example 1 says Mr. Walker applies a force of 100 newtons by pushing a box. Alright, so let's identify the action force. So in this case, the action force is, actually let me maybe type this out rather than write it out. It might be a little easier. The action force is Mr. Walker pushes on the box with 100 newtons. Notice that this situation involves two specific objects, Mr. Walker and the box. Mr. Walker puts a force on the box of 100 newtons, and that is the action force. The third law reaction force always involves the same two objects. Okay, so in this case, the reaction force would be the box pushes on Mr. Walker with 100 newtons. Okay, so I push on the box pushes back on me. Okay, and so if I were to draw the situation, here's Mr. Walker, smiley face. Here's a box. The FBD for the box would look something like this. Force of gravity going down, normal force going up. And let's say, just to make it easy, let's say there's no friction. Here I have an applied force from Mr. Walker. According to the third law, I put a force on the box is going to put an equal and opposite force back onto me. So what does my free body diagram look like? In other words, where does that third law reaction force show up? Well, it doesn't show up on the box. And a lot of people misunderstand the third law and they get confused because they think, well, if the forces are equal and opposite, don't the forces cancel out? And the answer is no, because they act on two separate objects. Okay, so one of those forces, the action force, is on the FBD for the box. the reaction force would be on the FBD for me. So if I do my separate FBD, I'm going to do it off to the side just so it doesn't overlap too much. But the FBD for Mr. Walker would have force of gravity going down, normal force going up, and then the reaction force would be an arrow going to the left. Remember, it's equal and opposite, so opposite meaning opposite direction, but the size of the arrow should be the same, and I'm going to call that FA, and guess what? That is 100 newtons. So if I put a force of 100 newtons on the box pushes back on me with a force of 100 newtons. Okay, now if that seems strange to you, imagine a situation, for example, let's say you're on like a frozen pond. And let's say, you're slipping and sliding along the pond and you come across a wall. If you push on the wall to the right, think about which way your body is going to move. If you push to the right, you're somehow going to move to the left. And you might not have thought about that before. That's kind of a strange thing. Like how is it that you're pushing to the right, but you somehow move the opposite way? Well, that has to do with what we're talking about here. This is just Newton's third law. If I put a force on the wall to the right, the wall puts an equal and opposite force back on me to the left, and so it's actually the third law reaction force that allows me to move in that situation. Okay, so it takes some getting used to, but the third law is not super complicated to solve problems with. Okay, so pause there and make sure you add that to your notes. Okay, so let's move on. Example 2. Mr. Walker hits a baseball with a bat. The bat puts a force of 5 newtons on the ball. So when you're doing these third law problems, it's always useful to identify the action and reaction force and focus on the two objects that you're talking about. Okay, because remember, anytime you're talking about Newton's third law, you're talking about an action and a reaction that only occur between two specific objects. So in this case, the two objects are the bat and the ball. The action force is that the bat puts a force of 5 newtons on the ball. The reaction force is that the ball puts a force of 5 newtons on the bat. That's it. Notice again, it's the same two objects. All we've done is, one force is going from the bat to the ball, the other is going from the ball to the bat, and it's going in the opposite direction. Okay, and this is one reason, by the way, why you experience what's called recoil. If you ever played baseball, if you hit a ball, you can feel it in your hands that the bat has a tendency to go backwards after it collides with the ball. Okay, and so the effect of recoil, which you also see anytime you shoot a gun, for example, that recoil is also a result of Newton's third law. Okay, if you imagine firing a gun, the gun puts a force on the bullet puts an equal and opposite force back on the gun, and so as the gun pushes the bullet one way, the bullet pushes the gun backwards, and so anyone who's ever fired a gun has experienced that recoil where the gun actually goes backwards towards your face. Okay, so you have to be careful with that. Okay, so that's another simple example with the third law. Okay, let's take a look at one or two more concept examples with the third law. Take a look at example 3. So example 3 says Mr. Walker stands on the ground. The earth is pulling him down via gravity with a force of 700 newtons. Okay, see if you can figure out the action force and the reaction force on your own. Okay, so I'm going to write this out. The reaction force is ... See if you can identify the action and reaction force on your own. Okay, and this question always messes with people. The action force is very straightforward. Let me put this in red so you can see it. The action force is the earth pulls Mr. Walker down with a force of 700 newtons. And what many people will say is the reaction force is something like the ground pushes up on Mr. Walker with a force of 700 newtons. But that's not actually the case. Or I should say, it is the case that the ground does push up with Mr. Walker with a force of 700 newtons, because of course the net force is 0. But that has nothing to do with the third law. Okay, remember when you're applying Newton's third law, you're focusing on the same two objects both ways. Okay, so if the action force is the Earth pulling Mr. Walker down, the reaction force is that Mr. Walker pulls the Earth up with a force of 700 newtons. And this is always highly disturbing to people. Everybody wants to know, how do you pull the Earth up? That doesn't make any sense. But it works the same way as the Earth pulling you down. You're not disturbed by the fact that the Earth pulls you down because you're used to it. But you pulling up on the Earth has the exact same mechanism. Gravity is an attractive force that attracts two masses together. We're just used to things falling down because of gravity. But we can also pull the Earth up with our own gravitational force as well. And the magnitude of that force would be equal and opposite to the force that we're being pulled down with. Okay, so the reaction force is my body pulls the Earth up with a force of 700 newtons. It has nothing to do with me staying on the ground, actually. In fact, if I was in free fall falling towards the Earth, if I'm falling down towards the Earth because the Earth is putting a force on me, that means I'm also putting, at the same time, a force up on the Earth. And technically speaking, the Earth would fall up towards me. Now, in real life, the Earth has such a massive mass, that the Earth doesn't move very much in that situation. So the effect is not really noticeable. But you do, in fact, put a force up on the Earth just based off of your existence. And so the FBD for that situation would look something like this, basically. All right, so the action force, Earth pulls a person down with a force equal to their weight. The reaction force is that the Earth, or the person pulls the Earth up with a force equal to their own weight. So it has nothing to do at all with a normal force. It's a little mind-blowing there. Yes, you can pull up on the Earth. Yes, that is possible. Okay, in this case, pull doesn't mean pull with your hands, but it means your gravity pulls on the Earth's mass, and because the Earth is below you, the direction is up. So it's kind of a weird thing to think about, that, but that is in fact a consequence of Newton's third law. Let's take a look at one more example. Okay, Mr. Walker is standing in the middle of an ice pond with a bag full of golf balls. Because it's difficult to walk on the ice, he throws the golf balls one at a time in the direction opposite the shore. Each time he throws a golf ball, he puts a force, there's a lot of typos here, he puts a force of 2 newtons on the ball. What is the reaction force for each throw? Alright, so pretend, let's say this is the shore here, and let's say I'm out here on the ice. I have no face. I guess I need a face. I'm sad. I'm on the ice. And I throw a golf ball that way. Now clearly in this situation, if I'm throwing it to the left, clearly my force is to the left. Okay, so there's an applied force of 2 newtons acting on the ball to the left. Now the third law reaction is of course going to act on my body, and so the ball feels a force of 2 newtons to the left. My body is going to experience a force of 2 newtons to the right. And of course, there's also normal force and gravity, etc., etc. But what's going to happen to me is I'm going to feel a force to the right, which means I'm actually going to go backwards towards the shore. And this is that recoil effect that we talked about before. The third law is entirely responsible for recoil. So as I throw a ball to the left, I actually move backwards to the right. And if I throw them faster to the left, I move backwards faster to the right. Okay, so which direction will Mr. Walker travel in? I'm going to travel towards the shore. And by the way, this also explains how astronauts could move in space, for one, because in space there's not really any frictional forces. And so if you're floating there in space, one way that you can move is if you throw an object one way, you're going to move in the exact opposite direction as your force because of Newton's third law. This also explains, by the way, how rockets work. And a lot of people have misconceptions about how a rocket works. They think it pushes off the ground or it pushes off the air. But actually, the way a rocket works is very similar to example 4, except instead of throwing golf balls at the back of a rocket, the rocket shoots out gas particles, and it shoots them out very, very fast, and because they're moving fast, they're very, very hot, and those gas particles move so fast, and they're so hot, and there's so many of them, that the third law reaction force acts in the opposite direction, and it allows the rocket to move. Okay, and that's also how rockets are able to work in space. Okay, so a lot of people think it has, to do with, there's fire coming out the bottom of the rocket, or it's pushing off the ground, but it has nothing at all to do with that. It's entirely a recoil situation. A rocket puts a force on the gas particles one way, the gas particles push back on the rocket in the opposite direction. It's like one big recoil situation with the third law. Okay, so I am going to, let's see, I've talked about recoil and rocket ships. Walking I'm not going to talk about just because it's kind of difficult to explain in a video, but I am going to share some videos with you that I want you to watch just having to do with some applications of Newton's third law. Really quickly, let me show you a picture. This is the skater pushing against the wall that I showed you before. The skater puts a force on the wall puts an equal and opposite force back on the skater, and so the skater recoils off the wall. And that's another example of Newton's third law. Okay, now before I get to those videos, I want to talk about one more thing related to the third law. Okay, so, or two more things really. So let's say I kick a soccer ball, my foot puts a force on the soccer ball. According to Newton's third law, the ball puts the same force back on my foot. How is the ball able to move? In other words, why don't the forces cancel out? Okay, so see if you can answer that question. Okay, so in this situation, the ball is able to move, and I actually answered this question before, because the two forces, the action and reaction forces, don't act on the same object. One force acts on the ball, one force acts on my foot, and so even though those forces are equal and opposite, they act on two separate objects, so they don't cancel each other out. Now here's another question. Which force is bigger? The force that the foot puts on the ball, or the force the ball puts on the foot? See if you can answer that one. Well, hopefully you got that correct. We've talked about equal and opposite forces this whole video, and so those two forces are actually equal. Neither one of them is bigger. Okay, the force that the foot puts on the ball is the same size as the force that the ball puts on the foot. One last question. Think about this carefully. Which object is going to accelerate more, the ball or the foot? The answer here is the ball. And the reason that the ball accelerates more is because the ball has less mass than your body, which your foot is attached to your body. And so I don't want you to think that just because the forces are equal and opposite, that does not mean they have the same outcomes. Okay, so let's do an example. Example 7. A 1,000 kilogram cannon fires a 50 kilogram cannonball with a force of 2,500 newtons. The first question says, which one is greater, the force from the cannon on the cannonball or the force from the cannonball on the cannon? Now, of course, if you've been paying attention, you know that those forces are equal and opposite. And so neither force is greater, both of those forces are the same. But one object does have a greater acceleration than the other. Okay, the cannonball has a greater acceleration compared to the cannon because the cannonball has less mass. And so imagine this happening in space just to make the FBD easier to draw. Let's say a cannon shoots a cannonball in space so we don't have to worry about normal force or gravity or whatever. I'm just being lazy with my situation here, but let's say that's what happens. So we have the FBD for the cannon, let's say, would go one way, 2,500 newtons. Or not the cannon, the cannonball. And the cannon, which I definitely cannot draw a cannon. Let's say something like this. That's totally cannon on wheels. For some reason, pretend that's a cannon. The cannon is also going to feel an equal and opposite force to the left of 2,500 newtons. So if you imagine applying Newton's second law to each of these situations, F net equals ma, of course there's only one force here, and so the net force is just going to be the 2,500 newtons. And even if this did happen on Earth and not in space, and there's gravity and normal force, it really wouldn't change what I'm talking about here. So here, the net force would be negative 2,500 newtons, because it's going to the left. The mass of the cannon was 1,000 kilograms. And for the cannonball, we did the same thing, but the mass of the cannonball was 50 kilograms. And the force here is also 2,500 newtons. So you see, hopefully you see immediately what's going to happen is even though the forces are equal and opposite, they don't have the same outcome. Okay, because the cannon is going to have an acceleration of negative, let's see, 2,500 divided by 1,000 is 2.5 meters per second squared. And the cannonball is going to have an acceleration of 2,500 divided by 50. Okay, so that's going to be 50 meters per second squared. And so the cannonball is going to have a much greater acceleration compared to the cannon, which is why the cannon flies out, the cannonball flies out of the cannon, and the cannonball, it goes backwards, it does recoil, but it doesn't recoil as much. Okay, so don't confuse equal and opposite forces with equal outcomes. Okay, so they both have the same force acting on them, but not the same outcome. The cannonball flies out way faster than the cannon. It goes backwards because of the recoil. Okay, so pause there. Before we end this video, I'm going to link a few more clips I'd like you to see related to Newton's third law. Okay, so please check those out. As always, please let me know if you have any questions, and I'll see you guys in the next video.